What we hope to cover during this webinar will provide not only a little historical knowledge, which we believe is key to appreciating some of the technologies that we're all exposed to on a daily basis, but also an insight into how they work, how they are best suited to particular applications, as well as a review of some of the fundamental physics behind their use. We will look at how we apply them to our measurement systems, as well as how to calibrate and understand where some of the principles, the variables and the constants come from and how they fit into that process. Finally, we will have a look at some applications of these truly amazing devices. We begin with a quick look at how we got here, the origins of these remarkable tools, and who was responsible for their invention. We have most likely all been exposed to some of the theories from Gauge, Sim and Ohm. The most common and best known electrical principle is that of Ohm's law. What he actually stated was that the current flow through any conductor is directly proportional to the potential difference, which we now refer to as voltage, and that is inversely proportional to the resistance. And so all three quantities are taken care of in one go. You may not be aware that this was something that he actually theorized in 1827. We now move ahead a brief period of time to the little-known Samuel Christie, who was actually the real inventor of what we now call the Wheatstone Bridge. In fact, he outlined the diamond principle 10 years before Charles Wheatstone published his paper on it. The problem was that while he was a reasonably well-read and recognized figure at the time, he wasn't as well known or had as many connections as Wheatstone, and the rest, as we know, is history. Some folks know William Thomson as Lord Kelvin, and it's very possible that if you've ever been exposed to any electrical theory, his name would have undoubtedly come up. To some degree, he did the same thing to Wheatstone as Wheatstone had done to Christie, by taking the credit for identifying that resistance changes in certain conductive materials when they are stretched or compressed. It wasn't until 1938 that a strain gauge as we know it today, or at least based on a similar concept, was introduced. Edward Simmons at Caltech conceptualized a simple extensometer. Initially, it was for impact test and surface deformation purposes. In fact, anyone that has ever seen a pendulum impact test will undoubtedly recognize that in Simmons' original patent application, which you will see on the next screen. At almost the same time, Arthur Ruge of MIT was investigating the effects of the earthquakes in Long Beach on structures and in particular water tanks. He needed something that could measure the stress on the tanks and apparently had a eureka moment and invented a strain gauge. There is a twist to these two gentlemen's stories, as they both tried to patent almost the same device at almost the same time. Ironically, they ultimately ended up working together and can jointly take credit for one of the most commonly used measuring tools in R&D. You can see both Simmons and Ruge's patent application illustrations on this screen. As I said before, I believe the Simmons version looks very similar to a pendulum impact test as we have today. A couple of things to do with these stories always makes me smile when I think about them. The first is that Gauge-Ohm's original theories were rejected by the German Physics Institute. They were recognised by the British Royal Society, the English equivalent of the German Physics Institute, and then of course adopted as fundamental principles by every scientific authority thereafter. The reason for the rejection was actually the nomenclature, the syntax, the verbiage, as some of his peers believed that he needed to change the words he used. Another interesting fact is that when Arthur Ruge submitted his design to the MIT Patents Committee, they stated, "The committee doesn't feel that the commercial use is likely to be of major importance," and declined to patent it. I wonder how much they would have earned in royalties if they had not made that decision. One final comment on Edward Simmons. I urge you to do a little research on him yourself, as he is the classic representation of the mad professor. Later in life, he attended meetings wearing a tutu, turban and tights. He became known as Dr. Strain Gage on campus. At the lower part of the screen, you can see some examples of some early strain gauges. You'll notice that the ones that on the left have paper backing. In fact, the original design was cigarette paper. There's little point in showing every step of the manufacturing process for strain gauges, but it is worth at least seeing some of it. Just knowing that the foil used for gauge manufacture is incredibly expensive is an interesting fact in itself. Although it isn't pictured, the process is based on about 5 stages: foil prep and layup, photo exposure, etching, washing, and then bonding or fixing. The next processes are all labour intensive. They're cutting and testing gauges. some of which have to be performed by hand on individual gauges. It is worth mentioning at this point that one of the factors that directly affect the strain gauge user is the determination of the gauge factor, which is also sometimes referred to as the strain sensitivity factor, or FS. As well as the type and grid design, it also varies based on the gauge material. For example, Constantin and nickel chrome have a transverse negative effect, while isoelastic materials have a positive effect. This can vary from gauge batch to batch. As we could see on the previous screen, the gauges are in sheets. Some manufacturers refer to these as batches. Because it is impossible and impractical to test every single gauge, random selections are taken from the batches to perform the required tests, noting that the selected gauges are effectively destroyed in the gauge factor determination process. On the point of transverse sensitivity, it is summarized by the Poisson theory for the material, but it is worth being aware that there is actually a transverse sensitivity in the gauge itself. However, this is typically completely ignored, as it is generally has insignificant implications. An interesting note is that the early adaptations of strain gauges were not subject to the same transverse effects, as they were typically round wire as opposed to the photo etch flats of today. As mentioned before, the testing is determined by randomly selecting gauges from the sheets or batches. These are literally mounted as you mount any gauge in normal use onto a very controlled test beam. In the image, you can see a large number of gauges mounted on the beam in the background. Another step in this process that is very labour intensive is the cleaning off of all the gauges from the test beam, and this has to be performed extremely carefully using non-destructive methods to preserve the integrity of the beam and the material and geometry of the beam. Now we get into the bit that we may want to know, may already know, or perhaps don't need to know, and of course maybe don't even want to know. But there is value in having a little bit of background knowledge for when the inevitable issues arise or somebody challenges you on what you really know. As we review some of the processes involved in configuring and measuring strain gauges, we will see a myriad of methods which can be used to get fundamentally the same answer. Keep in mind that almost everyone discovers the ones that work for them, and be assured that within acceptable limits, each will get you to the same answer. It is your choice which you find easiest to apply and most comfortable for you. Personally, I am a believer in the simplest, easiest approach, so if it looks simple, that's the one you may want to go with. Professor Sosi frequently stated that every engineer had to be a librarian. The last thing you want to do is spend all your time in the library. At the same time, consider the equipment that you are using. More modern and subsequently more powerful systems may well have all of the computational functionality to a large degree automated or built in. Older systems most likely had very little, if any. But that shouldn't stop you from wanting to know what is going on in the background, and having a reasonable appreciation for the maths and physics may well help resolve issues if you run into something. Let's start by looking at some of the fundamental stuff, the nitty-gritty, if you will, of how we use strain gauges. From here on, I'm going to assume we all know that a strain gauge without a bridge is kind of pointless. So what is a bridge? It's basically two voltage dividers. I'm sure we all know what they are, so I won't dwell on this for too long. But as with the image in the upper left, I'm pretty sure we would have seen these before. The bit we are interested in is, how do we construct a voltage divider into the legendary diamond form that Samuel Christie theorized in the 1830s? And to get this into context and perspective, by the way, the first electric light bulb system was demonstrated in 1835 by James Bowman Lindsay, which means Christie's theories were most likely documented under gaslight. The Wheatstone Bridge. A pair of voltage dividers that, when arranged into the so-called diamond configuration and provided with some known voltage, provide an equivalent voltage between them that is proportionally equal to the resistances in the dividers. A minute change in one represents a massive change in the global scheme of things to the measured output. We'll see later on just what that minuscule change amounts to. In the example on screen, you can see that the resistance on one leg has been changed. This results in an imbalance and subsequently a measurable voltage at point A. The other significant advantage with this arrangement is that you can pinpoint where on the bridge the change most likely took place, because the polarity will potentially follow it. We'll look at where and why later. In a perfectly balanced bridge, which of course we know is almost impossible to achieve without variable potentiometers or some other electrical mechanism, the measurement point represents as close to zero as it can. Like many measurements we make, we can use a process to manipulate that relative value to provide a second value for reference. We call this, in this case, shunting, and we'll look at that later. We can also take advantage of newer technologies to provide offset or imbalance compensations mathematically in real time. We should also mention that if the adjacent resistance has changed by the same amount, the bridge would once again be in balance. The two 8 ohm values illustrate this. On the next screen, we can see a demonstration of the adjacent balance. In this example, you can see each resistance change and the corresponding effect that it has on the output. The rule is simple. As long as the divider that you are using is matched, you should be able to balance the bridge. Switching in two opposing shunt resistors at the same time would also balance the bridge, but is generally impossible when you are using measurement systems, and frankly would be a somewhat pointless activity anyhow. This simulation, by the way, was produced using a free circuit simulator called Circuit.js Free, which is, as the name states, free. It's worth the download even if you only use it to prove your understanding of bridge principles. And it's free, so it's worth every cent. This short video demonstrates the use of the Circuit.js simulator to replicate how the various shunt values function and what happens when you change the resistance on different legs of the bridge. The changes to the resistance are unfortunately pretty coarse in this particular piece of software, but it still demonstrates the effect of the tension and compression of a strain gauge. Pay attention to the polarity changes as the variable potentiometers are changed. Now, let's take a look at the actual implementation of gauges, sometimes just one. We know this as a quarter bridge. A single gauge located on some sort of material, assuming that your measurement system will allow you to. I say that because some systems do not offer an input voltage to be practical on certain materials. For example, placing a strain gauge on a section of plastic would soon become problematic if the lowest excitation you could provide was, say, 10 volts. A strain gauge doesn't just look like a small electric heater, it is a small electric heater. Where there is a current, there is heat. The current is very small, but there is still heat. In some materials, the surface can be affected by the heat, and on plastics, it can literally mean that your gauge is now on top of a small lake. Ironically, this is something we have seen too many times. You may recollect the blue formula in the lower right from an earlier screen. This is another example of having a handful of approaches that you are comfortable with and keep them in mind. The formula can then be rearranged to suit the available information. Note the output based on the calculation would be around 0.5 millivolts per volt. That is based on the K being 2 and the target being 1000 microstrain or micrometers per meter, depending on your preferred unitless measurement system. Also notice that in the upper left-hand corner there is a clear indication that a quarter bridge cannot offer any thermal compensation. Let's take a look at the half bridge. It is a method of gauge application that can actually have multiple purposes. For example, the gauges could be placed in the same direction and effectively double the output, depending on where in the bridge you place them, since it is possible to effectively subtract the load from each other if you aren't careful about bridge locations. Or they could be perpendicular to one another and be used to subtract a parasitic component, or as in many applications, in a location where they won't be subjected to the loading conditions, but will be subjected to the same thermal events. In this case, they are a guaranteed method to remove the thermal component. In some cases, these are referred to as dummy gauges, as they are placed onto an unloaded specimen of the same type as the measured one. Pay attention to the bridge factor when you do your equivalent output calculations, as this is relative to your gauge arrangements. We'll review that later. But one that shouldn't be confused as a half bridge is the dual quarter bridge. This is two gauges in series on the same leg. In this illustrated case, the output is about 1 millivolt per volt. Again, assuming the arrangement is correct, since 0.5 times 2000 is 1000, and the units are microvolts, therefore the output is 1 millivolt per volt. The full bridge is by far the arrangement that would provide the greatest sensitivity, because as with one leg, changing resistance in a quarter bridge, the full bridge effectively could have all four, as you can see in the image in the upper left. And it has thermal compensation, as the opposing legs will be subjected to the same thermal events and therefore will subtract the thermal offset. In this case, the output will be 2 millivolts per volt, as there are now four components to the calculation. 0.5 multiplied by 4000 is 2000 microvolts, therefore 2 millivolts. Because we are believers in the simple approach to all these calculations, we actually want to simplify them even further. We can send you a copy of a spreadsheet that we put together that does all of these and a bunch of others that you're going to see. We'll talk about that at the end of the webinar. You may hear the words parasitic, dummy gauge, or even compensation arrangements. What these all really mean is that there are a number of layouts that can be used to accommodate all of these cases. In the lower right, you can see an equation normally associated with Poisson half bridge. The strain components are normal strain and the bending strain, even though the image shows 4 gauges. Unfortunately, I didn't have one showing just the 2. The shaft equation has the torsion strain component from a full bridge as per the image. The screen is really just to illustrate some of the alternative arrangements and types of gauges, such as the herringbone versions on the upper image. If the bending moment was considered parasitic, it could be removed to a large degree. One of the greatest concerns you may encounter is the thermal implication. The example in the lower left was suggested by John Miller, and it's actually a slick way of removing that effect from multiple points in one go, possibly in real time if your system can handle it. As well as the single dummy component, you could dedicate a single channel as a reference point. In this case, a dummy specimen is instrumented and measured along with the measurement points. This is then mathematically subtracted from all of the other channels as the data is being recorded. In this screen, I'm trying to emphasize the relationship between the polarity and the behavior of the strain gauge. As the gauge is stretched, that's in tension, the resistance increases and so the output voltage increases. If the gauge is squeezed, that's in compression, this reduces the resistance and the voltage decreases. I always find the comparison to fluid flows useful to explain resistance. If you reduce the diameter of a pipe, the flow is to some degree restricted. As you stretch the gauge, you are basically reducing the cross-sectional area, and so the flow is reduced. Inversely, if you compress it, the cross-sectional area is increased, and thus the fluid flows more freely. In this case, the fluid is, of course, our electrons. Ironically, early experiments were all done using some cylinders, which would be similar to the pipes that you use for fluid. And yes, I know that the bridge system in the water analogy would have to have the water flowing backwards at some point. But it's still a good analogy if you consider the flow from a restriction point of view. But nevertheless, I wonder how many of the early theories evolved because Kelvin, for example, saw that very analogy. Before we get onto the application side, let's have a quick look at wiring strain gauges. When you see a strain gauge, you will almost only ever see 2 solder points or 2 wires hanging off of pre-wired gauges. In reality, you could just wire your excitation and your signal return for a quarter bridge, that's a single gauge, but this creates a few significant issues, not least of all an absolutely guaranteed imbalance because your wires have resistance. Most modern systems offer at least a minimum of 3-wire connection. This is usually supported by a dedicated quarter bridge completion line. Some systems also have a sense line system, so on a quarter bridge, the 2 become 4. The benefit of the sense lines is the system will actually measure the voltage at the bridge and compensate for variations. These, of course, could be caused by thermal events on the wiring itself. After all, the wire is potentially being expanded and contracted by thermal events, and these may be some distance from the actual measurement location. When we look at some of the resistance changes relative to the output later on, it should put this into perspective. Knowing how they work is great, but actually using them is the ultimate objective. So let's take a look at configuring the various gauge and bridge arrangements. We'll use one of the most advanced software platforms to demonstrate a variety of different approaches. This first image illustrates a point that we made earlier about the perfect weld. As you can clearly see, there is an offset. This is always to be expected. If there isn't one, there actually may be something wrong with your bridge, although chances are, if there is, it will be railed in one direction or another, which should be a clear indication. It's always good to be able to see this as you're setting your channels up so that you've got a clear idea of where you're starting from. Starting with a method that is often associated with being a calibration method as opposed to a calibration check, although there will be times when this is as valid as almost any other calibration approach. The shunt method basically changes resistance on a leg of the bridge by a very accurate amount. Note the use of the word change as opposed to an absolute value. This would only be the case if the bridge is perfectly balanced out of the gate. We already mentioned that, of course, a couple of times, that that's very unlikely. The good thing about imposing a shunt value is that if the mathematical results deviate from what you observe, again, you have an indication of a potential problem. The calculation illustrated is probably the easiest one to remember. It's the go-to one that I use every time. You probably know the gauge resistance, Rg in the formula, the gauge factor, K in the formula, and you can add the bridge factor, Bf in the formula, based on the arrangement. One for a single gauge in this example, and the shunt Rs in the formula is whatever you have available to you on your system. As you can see, some more powerful systems offer more than one shunt, as well as options for locations to impose it on the bridge. This means you can check more than one leg. Using the calculation described previously, you can calculate what the equivalent should be. Using the formula we saw on the previous screen, and can see on the upper right of this screen, we can estimate mathematically what it is supposed to be, and then see what it measured. This is another formula that's available within the spreadsheet we spoke about previously. Some systems actually let you see the shunt value live as you test it, as you can see in this example. And if you missed it in this system, you can always switch it in later and view it from the main channel screen. If the system you are using is advanced enough, it may even give you a warning or some feedback on the result of the check. You may catch a deliberately bad value later on if you watch carefully. You'll remember the mentions of lead wire, something that was frequently set aside as of less than great concern in years gone by. Here, as with the ability to use multiple shunt values in multiple locations, some systems also offer you the ability to manually accommodate lead wire resistance and even measure it and tell you what it is. And by the way, just as an example, the 28 gauge 6 strand is typically about 6 to 7 ohms per 100 feet. An important aspect of this function is that it is primarily intended for the calibration step, as any variance in lead wire resistance can be accommodated to a large degree by taking advantage of sense lines where they're available. Notice the offset indication that was visible previously. Oftentimes this is something that is required as a comparison to the balanced value. From time to time you may encounter a sensor that has a shunt value related to a calibration performed on the sensor by the manufacturer. This is one of those moments where it would be nice if everyone agreed to say 174.5 k-ohm shunt was the standard, but alas they don't, and they probably won't, so here are some solutions. It may be that the sensor shunt simply isn't available on your system. Advanced systems have this incorporated into the software, as does the example you can see on the screen. In this case, you can enter the equivalent and it calculates the match for you, and/or the formula described here could be used as an alternative if you prefer to do this yourself, but just see what it was supposed to be and use that as a test to what you actually measured. This particular software actually reports the measured bridge resistance as well. In the field where you select the bridge value, it adds an additional note adjacent to it specifying what it measured. So if the sensor manufacturer forgot to mention what the nominal resistance was, you will have it readily available for your equivalent calculation. It may save you the need to make the phone call to the manufacturer in order to get that value. And by the way, this is yet another formula that's included in the spreadsheet. Hang around until the end to get information on how to get your copy. We already mentioned the Poisson ratio because it's an integral part of some calculations for certain gauge arrangements. This is to illustrate both where it came from and how you can calculate what it is if you have a test stand to perform the experiments on. We have also included in the lower right a proportional calculation based on known value targets using a Poisson formula if you need it. Ironically, a lot of folks use 0.3 as a reference, and it does cover a large number of metals. But as you can see in this chart, this number can change quite dramatically, even on what appears to be similar materials. For a later reference, you may want to make a note of the value for concrete in the upper left. Again, if the system that you are using is advanced enough, it will have an option to add these values or even simply select a material from a list. Notice on this screen the bridge factor is also available. The bridge factor is something that can cause some confusion as it relates to both numbers of measuring elements and the orientation of them. Some baseline typical numbers are simple to remember. A single gauge is always 1, unless, of course, you've got the gauge at some odd angle, at which time you probably should be looking at replacing that gauge anyway. Gauges in the same direction are usually simply the sum of the number of gauges, keeping in mind that you can effectively cancel measurements out if you wire them incorrectly. Perpendicular gauges are usually 30% of the primary direction. And so, as you can see in the illustrations, single gauge 1, 2 gauges in the same direction, wired correctly 2 gauges, 1 perpendicular to the other, 1.3, and so on and so on. Another great calculation to remember is the simple bending beam. The nice thing about this is that the formula incorporates both dimensional information as well as Young's modulus. It's a great way to confirm what you are doing is right, since this sort of test setup is one of the easiest to create in your own lab. In addition, recreating this experiment can help understand things such as bridge factor and Poisson ratio by simply adding more gauges, some of which could be perpendicular, than you could back calculate to the output. And again, as with most of the formulas, we have this one in the spreadsheet. Since we previously spoke about elastic modulus, or Young's modulus as most people refer to it, it's nice to see where the number actually originated. It is the basis for almost all materials-based testing. Without it, we have no benchmark for threshold monitoring. It gives us the markers that we need to determine whether something is within boundaries and are considered safe or less likely to result in, for example, a catastrophic failure. The nice thing about Young's modulus is that there are many ballpark numbers readily available. These can be found easily, but don't forget that material properties can change even during well-regulated and extremely consistent manufacturing processes. If the system is capable of performing the conversion, enter the Young's modulus and it can convert the strain to stress in real time. Stress equals Young's modulus multiplied by measured strain, the epsilon. This could be a large time saver, as this is one of the steps that could be required for many of the fatigue analysis processes that are often performed immediately after data collection. The rosette is a means of determining the principal stresses, strains, and their directions on your specimen, as well as almost any arbitrary angle they are in. It's difficult to determine shear stresses without these devices. Although the math is pretty intensive to resolve these, there is a good chance that your software will resolve these for you. In some cases, if the system is powerful enough, it can do this in real time as you collect your data. In these cases, I would recommend that you still preserve your original data, as anomalies can cause some confusion. Some systems record the original data as a matter of course anyway. Young's modulus is required if you're using rosettes, as results are typically resolved to stresses as well. Again, the math looks relatively heavy duty and you may never really care much for what is going on, but as with many of the formula associated with strain gauges, it's worth at least seeing it. Now, one point I would like to make while we're on this screen is that rosette gauges are all individual channels. Now, this may seem a little crazy to some folks for me to even say this, but you would be surprised how many times we get asked the question where a particular rosette element has to be installed in their bridge arrangement. If the system you're using is capable of resolving the rosettes in real time, this can greatly reduce your post-test analysis, as well as provide real-time feedback. This can be a substantial time saver, as you can see effects as they happen, as well as remove the need for extensive data processing post-acquisition. Some people who take advantage of this ability actually identify specific areas of concern and remove unnecessary gauges from their acquisitions as they go. This ultimately reduces the amount of data you have to manage, handle, and analyze after the collection exercise. In this example, you can see that the principal strains and von Mises are being gathered simultaneously with the original rosette strain channels. By doing this, you can check to see if there are anomalies and perhaps even rerun rosette analysis post-test. To round up the show, we'd like to share a few examples of gauges in action. It really is just to inspire new users and provide an opportunity to see how other folks are using them. The classic application for strain gauges is, of course, transducers themselves. In fact, you can consider any strain gauge that's laid onto any specimen as effectively modifying that specimen into a transducer. An interesting fact is that the ratio of strain gauge-based sensors to all sensors used today, not including temperature measurements, is well over 50%. Pressure sensors, load cells, wheel force transducers, some accelerometers, and a myriad of other types are basically strain gauge devices. As an example, in a wheel force transducer, the number of strain gauges can be many tens of gauges. The example illustrated has 32 gauges visible in the drawing. The photo is a Michigan Scientific wheel force transducer on a motorcycle. It's worth noting, of course, with wheel force transducers that most of the wheel force transducers resolve the forces of moments for you, so you're not actually measuring a strain gauge per se. The custom load cell example in the upper right has a mass of gauges to remove the parasitic components and provide the greatest output in the axis in which the device is intended to measure. As you can see, there are a large number of gauges mounted on it. The load or pressure sensor in the lower left illustrates the gauge layout to achieve the maximum output for surface contact. Some sensors similar to that one actually have circular strain gauges to cover the entire area available for the measurement. The example on the left is a military vehicle with gauges located on the frame for durability monitoring. There was gauges actually placed all over this particular vehicle. The one on the right is an aerospace application that has a mass of gauges in a fairly small area and really just illustrates the need to get elaborate for some measurements. In these images, you can see the surface preparation and the care taken to align the gauges in a specific orientation. The directional outcome is rather meaningless without precise knowledge of the individual element's alignment in the first place. Some software actually has pictorial references to these, as you saw earlier, so that you can actually relate them back to the angle pictorially as well as by the reference that you've applied to them. Another point of interest here is the placement following the rules regarding the placement of the gauges to welds. We all know the weld is likely to be an early failure point, and placing gauges too close to them has a number of implications. One of which is that if a gauge is atop a crack, it won't see loads the same way, as the crack has already relieved the material of the loading effects. The other one is that welds cause changes in the materials that are typically very localized and can initiate microcracks due to the thermal contractions. The individual gauge on the lower right may well have been placed because previous testing had already identified the angle with the highest load. Shear was probably already previously described, so a single gauge could be used to reduce the total amount of data collected. John, one of my fellow app engineers, is very proud of his micro-measurements training specimen, and so he should be. You can clearly see that he went to great lengths to ensure surface prep was thorough, and honestly, that is some of the best soldering I've seen in a long time, assuming they weren't pre-wired gauges. The other examples on this screen are also compliments to John with his civil engineering background. He has been called upon many times to help with instrumentation on projects where materials such as concretes are involved. You may remember my reference sometime earlier regarding the Poisson component differences. Those unfamiliar with this sort of gauge work will probably notice that some of the gauges are extremely long. This is because of the properties of the material, and it reinforces the aspect of gauge selection in respect of the material that you plan to apply them to. The surface structure and density of concrete is a macro version of aluminum and other alloys, so the gauges grow proportionally in length to the structure. As you can see, some of the gauges are embedded in the concrete to determine the properties of that particular mixture. You may see similar embedded uses of carbon fibers and some plastics, but keep in mind that strain gauges and temperatures, well, they don't mix very well. Only with specialized gauges can you place a gauge into something that potentially was molten, such as a plastic, for example. So be careful about gauge selection when performing those kind of exercises. The shafts that you see in the upper left and center are examples of measuring strain gradients on very different materials. Again, note the significant difference in gauge length between the two examples. In the lower left are Rosette gauges on a roller coaster used for dynamic analysis of a bracket with previously observed failures. It's nice to know that they were looking into the cause, hopefully with the intention of preventing any accidents. The lower center is actually a homemade transducer. It was used to determine damping coefficients of various materials for dropping large weights in a workout area. I wonder if the large weights were the people who possibly needed to be in the workout area. The lower right is a strain gauge project involving a utility pole measuring strain and stress of it as the sections were seated into one another. The master gauge applicator you see is actually our very own John Miller, although he claims anonymity by wearing the proper safety equipment, which I guess is a good thing. On the left, you can see another view of the same utility pole, as well as John attempting to photobomb in the same white helmet in the background. It illustrates the precision with which gauges need to be placed even on large specimens. The final image on the right is an aerospace project, which, as with many high-cost installations, has a massive different sensors applied, some of which, I'm told, are strains. I can't personally see them, but that may be a good thing. Matt Enquist provided the image and assures me there are gauges in there. And so we're going to open the challenge to see if you can find them in that jumble of cable, sensors, and hardware. So this is the final screen, and it's basically the spreadsheet that we've alluded to a number of times during the webinar. It contains virtually every calculation we refer to during this webinar, as well as a couple of others. And each are illustrated with a pictorial representation of the application, and the values in each of those images is updated as you change the parameters. So you get a pictorial representation of what you're doing, and hopefully that'll make some of this a little clearer. So if you would like a copy of this rather useful spreadsheet, just contact your local representative or the support guys, and we'll be happy to pass it along to you. Now, it doesn't contain any macros, so it probably won't get stopped by a firewall, so hopefully you'll get your copy.